Then even though there is some disturbances in the channel, so you can check this. Is it audible? Ah, okay. Okay. Check this. So that's what we take like two symbols for analysis. Like our aim is to nullify that inter-symbol interference. So for that purpose, like what researchers have decided means they want to keep some time gap between symbols. So if you are so what to put? So if you are giving some time gap between symbol to symbol, what to keep in that symbol? Like some like we don't know like what to keep. So suppose we are not keeping anything, there is the problem for amplifier. Check this one, this slide. Like what to put means like if you are keeping nothing in that gap means there is a practical issue. That means what happens means in a wavelength system that we need to amplify the signal. If nothing is there means there is a severe issue for the amplifier. For that, what researchers did means OFD modulation technique, they copied the last part, some part of it from the tail end, and they pasted into the front end. So that means they copied some part of the original transmit symbol to the prevent. So this is called type of prefix is called psychic prefix. Because of that, like we know what is the boundaries of symbol. Yes. Because of the psychic prefix, we can avoid inter-symbol interference. Apart with that, we can also get the other benefit is we can find what is the symbol boundaries. Like in reality, like if you want to know what is the difference between how to identify symbol boundaries means if you are finding the correlation between symbol one and next symbol, you will get high correlation. If it is high correlation means that is exactly good symbol. If the correlation is less, that means you need to think of that it is not the proper symbol boundary. Again, in case of symbol boundaries, like you know what is the pattern of symbol. So whatever the like end bits that are dependent into the which side, so it is very easy to find this. It is like overall the block diagram OFDM. So in general, what happens means in OFDM, so whatever the data we are having, that means this data means maybe our signal, that is voice signals, and we can take our audio signals, or it may be whatever video signals. So whatever the data we are having, those data will be given to the like as input, that is called the meaning of data in. So that is in reality. But in practice, what we will do means while simulating our result or while checking our results with the accurate one, we will generate some random data. So that is based upon our requirement, like based upon number of sub carriers, like what is the frequency mode, like how much frequency we are using, what type of those things we will consider, and based upon that we will generate the data. The data is entirely random. That is in terms of ones and zeros. So after what we will do means by using modulator, like we are having various modulation techniques. Everyone is studied this. So based upon that modulation technique, like we are having BPSK, QPSK, like if you come to the hierarchy, we are having 4 form, like form techniques, 16, 64 like that. So based upon like our requirement and like what like we want more bitter rate, like you want what parameter we are aiming. So if you want to aim, you need more reduction of PAPR means we need to find we need to use less modulation. That means order of 4, that is either 4 form or QPSK. Or if you want more bitter rate, that means we go for higher order modulation scheme. After that means now whatever the data we are having, that one we are mapped using modulation technique. So after that data, we will give it to the IFFT. IFFT means simply inverse fast Fourier transform. What it will do means, like whatever the data we are having now, that is in frequency domain. That one, with the help of this inverse fast Fourier transform, we are converting into the time domain. So this entire data now figure means this is in digital domain. So once we are converting the data, like this applying ISF means that one we will give to the digital to analog converter. That means it will again like in reality, whatever signals we are having, that maybe voice signals, audio signal, everything is analog in nature. So while transmitting the data over a channel, we will again like whatever we are doing inside the system, like transmitter end, at the end of the day, that means before transmitting the data over the A, we will give it to the like we will convert it to the analog domain. That is called sometimes continuous time also. So we will convert that data, whatever data we are having now up to now, digital data, we will convert into the by using digital to analog converter. So now whatever data we are having, that is analog. So that data we are transmitted over the air with the help of antennas. Like again, in the channel, we are having various channels. Like ideal case, most of our, like in case what we will do means, we will consider L2 white Gaussian noise channel. That is ideal scenario. But in practice, we are having various real-time channels, like pedestrian channels, vehicular technology, like extended vehicular channels, like delay Doppler channels. Like we are having various channels. Like those channels, how you are performing, that is the main thing. That is like that is a transmitter part. Receiver part is exactly like vice versa of this transmitting part. So whatever we are receiving here, that means after channel, the data is again analog in nature. That data again we want to receive, right? So for that purpose, we will convert that data. That is whatever the data we are having in analog domain. Again, we will convert with the help of analog to digital converters. So now the data is in digital domain. So with the help of again, like now the data is in time domain. Actually, we are sending the data in frequency domain. So to cut back that one, we will apply for fast Fourier transform. Here, what will happen means, so actually the previous one is the result in time domain. So with the help of FFT, we can convert the time domain into frequency domain. Later, with the help of demodulation, that means based upon that, like received data, we will map the symbols and that data will pass to the receiver. This is about a simple block diagram OFDM. Like why I'm explaining this OFDM is maybe 10 years back technology means even though it is old technology, still like even 4G OFDM only used. In 5G also, in case of uplink, only OFDM is used. While coming to the downlink, in practice they used cycle prefix OFDM and single carrier FDM used. Now, like it is in the era of 20th era, like in case of 21st century, actually, this OFDM is like not giving proper result. Why? Because in case of OFDM, we need to maintain orthogonality. Like orthogonality is one of the big issues. Suppose if something is happening in channel means you don't have any control on that. So now the like vehicles if you observe means these are all fast moving vehicles. That means at least the speed is more than 50 kilometers per hour. So in that scenario, our OFM is not able to give the proper result. Why? Because the subcarriers like they are not maintaining orthogonality of subcarriers. Orthogonality means that whatever even though we are having many number of subcarriers, only one subcarrier which is having non-zero value and remaining are zero value, but that is not maintained if the orthogonality is used. So for that purpose, in for next century, that is for 6G communications, that is for 21st century, researchers are trying to find various waveform techniques. That is another one is OTFS. What it is, this is like second like waveform technology. That is OTFS. OTFS stands for orthogonal time, frequency, and space. Actually, it is a two-dimensional technology. Before going to this actual waveform technique, you will explain like overview of what I will present this second waveform technique. I will give like introduction of like OTFS, what is the need of OTFS, and what is the main objectives, like what are the previous works that has happened in related to OTFS model, and like we do like here also like OTFS is one of the multi-carrier technique. So because of that, there is a problem of PAPR. That means like all this multi-carrier modulation technique, PAPR is one of the issue. To avoid or at least to reduce that, we will try to apply like we applied compounding technique. So because of that, what happens means even though the strength of signal at the transparent is high, with the help of this compounding, we can compress that signal. So after we will see one bar, the similar results, followed by conclusion. For this part, you can check this. Actually, next generation wireless systems are expected to support various scenarios, including high-speed trains, vehicle-to-vehicle communications. Nowadays, like people like who are going like by via planes, they want data. So they suppose some person is going from India to maybe USA, he has to stay like, in flight at least 24 to 48 hours, depending upon the route. So for that is like the user is unable to sit without data. For that purpose, whatever the existing technology you have in OFDM is completely failure. For that purpose only, like not only for that purpose, like check the bullet trains, the speed of that train is more than 400 kilometers per hour. In that scenario also, our OFM is not giving a fruitful results. That means the argument whatever it is maintaining, it is not maintaining that. So because of that only, we are going to like this technology that is OTFS, that is orthogonal time frequency and space. Coming to this, but it's clearly like OTFS stands for it is an orthogonal time frequency space. It is a two-dimensional modulation technique. That means two-dimensional means like we are having like plane structure, we are having x-axis and y-axis. You can check these here. The information symbols are multiplexed in delayed Doppler domain. How multiplex these information symbols in delayed Doppler domain means we observe this. Actually, this ODFS transforms the time domain, like this whatever the channels we are having, this time varying multi-path channel, into a time dependent two-dimensional channel. See, actually, this time dependent and the delayed Doppler domain. So whatever we are placing delayed Doppler that reflects various reflectors in various dimensions. Suppose if you observe the first figure, you can check this on white, that is base station. You don't know the base station. The gray vehicle, like the suppose we are assuming that the person is available, who is using the data, like who is acting as receiver, who is setting this one means gray car, we are assuming the person is a receiver. Now you can check this. There is a direct path between user equipment to base station. That means in the case what we are assuming means it is a direct path. Even though it is some delay, there is this prop distance, there is some delay, but this is the first component it is receiving. So on that basis, we will keep it as delay is zero. Since the vehicle, like the user is moving towards the base station, that means it is having some Doppler values, but it is moving towards the base station. So that is the reason we will keep some positive one. Again, you can observe the strength of that path. So since it is a line of sight path, it is having strong connection. That is the reason I am keeping more strength in terms of blue. Coming to the other way, you can check the yellow color. Like it is having like there are reflectors actually. That reflectors like is also moving towards our base station. That means what happens means since it is moving towards the base station, like it is also having some Doppler. There is also again positive Doppler. But since the propagation distance between this compared of receiver, the reflection having more propagation distance. So because of that, we will receive less strength when compared to the random set path. Coming to other reflector, you can see the draw in another lane. In that lane, you can clearly see that like that vehicle is moving away from the base station. Since the vehicle is moving away from the base station, it is having some Doppler that is clearly negative. So that is the reason we are keeping that is having negative Doppler and remaining two reflectors and line of sight positive as positive one. So in this way, we are mapping the symbols in the delayed Doppler. Next, second picture is again we are taking after some time. So for the analysis, I took after 10 seconds. We can observe that again it is having user equipment and base station. Since here also like same setup, here this is a direct path we can observe this. It is also moving towards base station. That is the reason I am keeping positive one. Next one is yellow, like this similar but it is somewhat near to base station. That is the reason we are having more Dopplers. Next one is now you can see that truck is moving. We are getting some other truck. So because of that, we are getting negative Doppler bands. So in this way, we will map the symbols from data to delayed Doppler grade. So you can check these, like that means what are the paths, like each path in a delay domain, is delay Doppler domain, correspond to cluster of various reflectors with specific delay and Doppler values. That means the delay Doppler values again, we are finding that one means that is depends on various reflectors and relative distance between the transmitter and receiver. Again, we are assuming that by measuring, we are assuming that the path having at least is a constant up to some milliseconds or microseconds. Again, if you observe this, we are assuming that the channel is having, it is producing constant velocity, means we can treat it as quasi-static. In that case, the channel has very few parameters. So, this rotatless model can be represented as a sparse case. That means it is having more number of our terminal having more zeros compared to non-zeros. So that is the benefit of this. So because of this sparse representation, this OTF is having more number of applications than OFDM. Again, this OTFs, we are handling the data directly on delay and Doppler domain. That means there is no impact of now Doppler or frequencies. So that is one of the good ability for this modulation technique. The main objective of this OTFs in this work is we need to reduce the PAPR, peak to average power ratio present in the OTFs signal. Again, while reducing the PAPR, we need to minimize bit errors. That means, suppose if you are reducing one parameter, means definitely it is affecting on some other parameter. Here, if you are trying to reduce the PAPR, means it shows some impact on signal. That is actually receiving a signal. Because of that, whatever the signal we are transmitting, we are unable to receive that one. So because of that, you may get more bit error rate. So that is the reason. In this case, the objective of this work is we need to reduce the peak to average power ratio while maintaining tolerable bit error rate performance. Again, in this work, we explain we will try to demonstrate the amount of PFA is reduced before and after compounding is almost same. Some of the works related to this vortices are there. You can check this Surabhi GD. She is from IISc Bangalore. She analyzed what is the PT average power ratio in OTFS modulation. That means she characterized the OTFS in peak to average power ratio format. She analyzed what are the various issues in OTFS. After that, she formalized that peak to average power ratio is one of the issues. So for that purpose, she wrote one paper. So after that, in second part, like Gaussian or Nuttall, they reduced the peak to average power ratio with the help of iterated clipping and filtering technique. That means what happened exactly in that work means they are trying to reduce, suppose in case of OTP signal, it is having, it gives various power levels. The highest power levels, that means we will keep this is the threshold value. If it is having more than that, it will clip. But that clipping is not done at one instant. It will be done through various iterations. Why? What is the need of this iterations means? Suppose if we have clipped the signal at a time means what happens means there is a possibility of getting more bit error rate. So to eliminate that part, we will do means we will clip the part step by step. Because of that, we will estimate what is the bit error rate at the end of the receiver. So because of that, every each stage we will clip the signal that and after we use it to filter. So that is the second bar. Coming to the third bar, that is exactly they use PPR or to reduce the PAPR, they use compound technique. In that one, they used Muller compounding. Actually, Muller and Ela are everyone knows that they are famous techniques. Why? Because Muller and Ela are used for audio compression and enhancement. So after that, in fourth one, I gave that work, I did that work, Anandra Petra and Palani Saman. We are targeting with the help of normalizing versions of Muller and Ela compounding. So in that we got some good results, when compared to actual Muller and Ela compounding one. This normalized Muller and Ela giving fruitful results. That means we are reduced, we got some good results in terms of PT average power ratio. And at the same time, the reduction of bit rate, the bits, that is, we are losing, the amount of information we lose is that is very minimal. So for that, like we are taking that one is basis, we are trying to implement for various routing campaign techniques. So whether this campaign, like that means OTFS is supporting this routing techniques and all, we tried. Like based upon that one, we got some results again. Those results are published in this journal, International Economics. So these are some of the literature we are having. We can check this. Like some simple techniques to reduce the PAPR, like I'm considering only two, but there are various techniques are there. The first one is clipping. That means to reduce the PAPR, the simplest way is user having some sinusoidal signals, just will clip the top of that. Suppose if you are clipping that more amount means here that amount of information we are losing at the end. So that is the reason only if you are clipping something, you need to know how much value you can clip. So based upon the clipping technique only, like more amount of error we may get. So that is one of the issue. That means by using clipping, we may get more PAPR, but at the cost of bit error rate. Next one is the compounding technique. What we will do with this compounding means let the transmitter and again our communication means we are having only three part blocks, everyone knows that. Transmitter, channel and communication like receiver. In transmitter, the transmitter with the help of compounding we can compress the peaks. Whatever the peaks that come to the transmitter end, therefore decoupling, we will enhance that one. So while doing this process, that means compressing and enhancing peaks, we will not disturbing the average power. If you disturb the average power means that is one of the issue in meter. So we are not disturbing the average power, we are maintaining the average power before and after. So that is our goal. Now that purpose only, like we introduced here, like our proposed one, like you can check this at the transmitter technique. At the transmitter, like we are, like you can check this block diagram of this 40 bells. It is very similar to the OFDM, except this side, it is having some pre-blocks and post-blocks. So we can call it as sometimes this OTFS is a pre and post coding of OFDM. That means by applying like so it is you already deployed this OFDM technology base station. So it provides some like compatibility to the OFDM. So you can check that the transmitter part. This is the binary information data. Whatever the data we are using nowadays, it is entirely we will convert into the binary data only. So that data we will map with the help of this mapping technique. Here we can use any mapping technique we like. In general, we will use 4-form, 16 or 64 character. So after these techniques, like these symbols, we are mapped. That means we are keeping these symbols in delayed development. So that's what we explained to you. So now to map like to convert those signals or we can say symbols from delayed Doppler grid to the time domain, we will use inverse symplectic finite Fourier transform. It is actually a two-dimensional technique, like you know, like one-dimensional techniques like IFFT, FFT. But it is a two-dimensional technique. What happens means you can say ISFT is a combination of IFFT and FFT. That means once we are placing the symbols in the related of the domain, those symbols we have mapped into the time frequency domain with the help of this inverse symbolic finite Fourier transform. Again, this ISFT has various applications in our signal processing and wireless communications. Like after that, once we converting the symbols in time frequency domain, now our aim is to convert into the time domain. For that process, what we did means we applied OFDM modulator. That is the generalized version of this OFDM modulator is nothing but Heisenberg transform. So what it will do means Heisenberg transform is nothing but simply of IFFT. It is a modified. and that data we are transmitted with the help of windowing techniques. In general, now we are saying that this OTFS is a pre and post code version of OFDM. So we will take rectangular signal like rectangular pulse in general. That is what this transmit windowing is. Like it will act as a filter actually. So after that, whatever the data we are having up to now is a parallel. So what we will do is now we will convert that data into serial fashion. So once we are doing that, so that means to convert that parallel to serial, we will apply vectorization in MATLAB. So after that, again we expect this concept. So we are sending the ashes like after converting serial data means there is a problem of inter-symbol interference and inter-carrier interference. So to eliminate that one, we will apply here also. So to eliminate that one, we will use cyclic prefix. So by applying cyclic prefix, we can eliminate that inter-carrier interference and inter-sample interference. Now this signal actually this is the body of a signal. So this signal having various levels of peaks. So if you want to find the power at this point, it is having various power levels. Actually, this OTFS also belongs to the multi-carrier modulation techniques. So because of that, maybe having high power levels. It may be order of some maybe 10 watts also. So if you are sending those power levels means it is very difficult for the amplifier to amplify like that. That means our amplifier is not operating in the linear region. So if our amplifier is not operating in the non-linear linear region means it is not properly working. So for that purpose only now after adding cyclic prefix we apply compounding technique. So in this one we are using like various compound techniques. The job of the compounding is very simple. Like we are having various peak signals. Now this compounding it will comprise the peak signals. So after compression of those signals, now the compression version of ODFA signal is transmitted over the air. Air is nothing but channel. So here, actually this what we said means this clearly ODFS is handling high Doppler and high delays. For that purpose, we implemented like we are considering various real-time channels. Like I did for both like a real time and ideal case. Ideal case means we will apply AWL channel. In reality, we will take double dispersive channels and delayed Doppler channels and extended Baker channels. For these three channels, we implemented, and I will bring here some of the results also. That is about the transmitter part. Once we are sending the signal over the like the transmit data over the it means that next step is we need to receive the data. So this data is now, if you observe, means this is a compression version of this transmitted data. Now because of this channel, various reflectors in the channel, whatever the data we are transmitting, we may not receive at the exact time. It may be something maybe because of various phase shift, various path losses. Now this one, now first step is we need to enhance whatever the data we are compressing at the transmitter. We need to enhance that one. So for that purpose only, we apply inverse compounding transform. So after that, the transfer part, we add the cycle prefix. Now the job is we need to remove that one. Right? Means we need to send, like we need to receive whatever the data we are transmitted. That data only we need to receive. So for that purpose, we remove that cycle prefix. Now until now, the data we observe means it is serial in nature. Now to map that one, we apply onto parallel data. So we are converting the data from serial to parallel. Once we are converting to the parallel one, we apply the nothing but OFM demodulator. OFM demodulator we also call it as like visual transform. It is simply nothing but FFT. So after that, to like that means now the data is in time frequency domain. Now to map the data from time frequency to the delay Doppler domain, we use simplified Fourier transform. So after that, with the help of demapping means inverse modulation techniques, we map to the output. So in this way, we will estimate the difference between actual input P and we have, that is output. If there is any class, that means if there is any mismatch in data means that is nothing but how many number of bits that are coming error. So on that basis, we will find the bit error rate. But the same thing, whatever I explained through block diagram, the same thing is mentioned here for another for understanding. The same here. Like here you can check this. This is the proposed one. Like the proposed combined transforms. Like here, it is simple. Like everyone knows this and hyperbolic technique. So we are like whatever we study during our BTech, maybe MTech. So that technique, like this tan hyperbolic compounding, tan hyperbolic one, that one we will apply as a compound technique. So what is the use of this one means? We can check this clearly. Like because of alpha, you can check this. This alpha c times tan hyperbolic of actual transmit signal by this compounding parameter times signal function. Where SI here means sigma. Everyone knows this is sigmoid function. Now you can check this. Now this alpha is a normalized parameter. It is nothing but square root of our average power levels. You can say square root of mean values, this signal to the whole one. So this is one we applied at the transmitter. So because of this, we got some less peaks. That means even though we are having high peaks of signal, the strength of the peaks are reduced. Now at the receiver, you can check this. So we are receiving the data that is nothing but R equal to H times U plus W, where H is nothing but our channel matrix. Like we know various like how to map the channel matrix and all. The channel matrix consists of various channel parameters, various propagation delays, fall delays, and reflectors and all. Like we know how to develop that channel matrix. Like here only our main picture, main theme. Like what is the channel? Like what are the parameters we need to consider? How much Dopplers will they having? How much speed we may get reflectors? So all those things like line of sight path, non-line of sight path, all those paths we will consider. So based upon that only we will decide what is the channel is. Now we can check this. So now we decide that this channel is having is a grid of a channel. So after that, again, we need to enhance the signal. For that purpose only, we applied this decompounding one. But the decompounding is very simple. Where for compounding one, we use tan hyperbolic. So we will use tan inverse. So that is what tan inverse one. Now, after that, again, we are mapping the data from time domain to time frequency domain with the help of that Wigner transform. Later, with the help of this symbolic Fourier transform, we are converted from time frequency to Doppler domain. So this is like affirmation. This is our signal terminology. Everyone knows that. Finally, what are the data symbols that are available in DD domain are serialized into sequence and then mapped back to the actual binary data. So this is how we did that one. Now we can check the results. Like what are the results? Like what the output we got. The first one is the power levels. Like how we are finding these power levels means the first one, like you can observe this, here we are having three graphs. The first one is actual ODFS signal. The next one is tangent compounding technique. The third one is Mueller compounding. Now you check this, the amplitudes. The first case, you may get around peak signals, you can check this, is around 17 to 18 watts. But when come to proposed one that is red one that is tangent compounding technique, the peak values are reduced to around 5 to 6 in between. That again, when compared to the green one, you can check this Mueller compounding one. So when compared to Mueller compounding also, the proposed one that is red one is giving less number of peaks. That means it is strength is reduced by applying compounding. So In that time, we are reducing the peak values. Now this is another metric like to test like it is a value comparing one means or value technique means. This is one of the metric that is CCDF. This CCDF stands for complementary cumulative distribution functions. Like we know everyone studied distribution functions in probability theory and statistical process. Like we are having various Gaussian density distribution, parallel density distribution. Like that, to to analyze our communication in communication, like system is one of the main tool. What it tells means like how we are doing this one means we will consider various number of independent frames. So like in case of power levels, we consider only single frame. But here we consider like this, we will generate maybe 10,000 samples, maybe 1 lakh or more than that also. So with the help of those number of samples, like those number of frames, like every frame we are considering is independent. That means we are not combining with that. So based upon those multiple number of independent frames, we will measure this CCDF. Again, how we measure means with respect to some threshold value. Now we can check this, the results, system of PAPR. But this is like we analyzed for where n is number of couplers, m is number of delays. Here we use four-form modulation technique for simplicity. So we can check the system of PAPR. The blue line indicates the actual signal. That means while we drawing this on system plot, we got the blue plot. Now, if you observe means it is having more. So for that, we need to reduce that value. For that purpose only, we applied our proposed tangential compounding one. So by applying that, we are reducing like actual audible signal. We can observe this is around 5 dB. That is the like achieve like we achieve. Whereas the existing one, like Mula one is existed, that is developed by like Naveen Kumar, like is not like around 4 dB. So because of this tangential tangent compounding, we got more reduction of PAPR than the existing one and actual one. That is one scenario. Suppose we cannot say like we cannot conclude that based upon one scenario. So for that purpose only, we again go for some other scenario. In that scenario, we are considering 32 Dopplers and 64 delay beams. Again, for simplicity, we have taken only four modulation. In this scenario also, the proposed one is the dimension compounding one gives the best result compared to the actual one which is there in blue color and the existing one that is green one. So because of that one only the proposed one is giving the fruitful one. That is in terms of PAPR. What about bitter rate? In general, if the PAPR we are getting like more reduction of PAPR means we are compressing the actual transfer signals that much strength. So now we will check the like results like in terms of bit rates. How much like by compressing the actual data, how much errors that means between transmitter and receiver we are losing. That means we are receiving the errors. We can check these. This is plotted the first one for A. So it is plotted for 16 Dopplers and 64 delay beams using 4-form modulation technique. So we observe this like the traditional one, that means actual ODF signal always gives the best one, that is the blue one. Now the proposed one, you can see in red color, that is giving after the actual ODF signal, the proposed one is giving the best bit rate. After that, existing one. Now you can observe the previous result system of PAPR and this one. So here, the proposed one is giving better bit rate than existing one. You can check the previous one. Here also, when compared to the existing Mula, the proposed tangent compounding gives best reduction of PAPR. So based upon these two factors, that means it is giving best reduction of PAPR as well as best providing better bit rate performance when compared to the existing one and actual potential signal. So that is realized for single scenario. So what about for some other scenarios? So we analyze second time, like second scenario by considering 32 dollars and 64 delay means. The same thing, like we have almost got the same results. Again, in this scenario also, the proposed the financial compounding one gives the best production of credit performance than traditional one and the existing new level. So because of these two factors, we concluded that the proposed compounding gives the better production of PAPR. Again, it gives not only best PAPR, reduction of PAPR, it is also providing like irrespective of scenarios, maybe 16 dollars, 32, or it may be extended to 64, whatever, 128. Irrespective of number of delays and Dopplers present in the channel scenarios, the proposed the initial compounding gives better direction of PAPR as well as PTR. Again, like other modulation techniques, like other compound techniques, for this tangential compounding, there is no need to maintain any trade-off. Some of the references I used to like the paper.
After 10 minutes again we can join.